this question says nitrogen monoxide here reacts with oxygen to produce nitrogen dioxide. This is a gas phase reaction in the sense that everything is a gas at all times. We have 2 moles of nitrogen monoxide, and it reacts with 2 moles of oxygen to produce, to produce the nitrogen dioxide. This happens in a container with a given volume. So we have V. We have a temperature which is equal to 298 Kelvin. So you already know, convert that to Kelvin. When the reaction is over, what is the total pressure? So we're assuming that this is not an endothermic or exothermic reaction. We're not worried about temperature changes. We're also assuming it is, they're going to act ideally, even though these are not technically ideal gases. They act well enough like it. So all that to say, it's going to be an ideal gas equation. PV equals nRT. But it says, what is the total pressure? So using our math rules, we're going to divide both sides by V. And that's going to give us P equals nRT over V. Ultimately, we want to get to nRT over V. We know R is 0.0821 related to liters and atmospheres and mole and Kelvin. That's just the constant. We know the temperature is assuming it's going to stay at 298 degrees or 298 Kelvin. You don't technically say degrees for Kelvin. So 298 Kelvin. And we know the volume is going to stick with being 25 liters because it says a rigid container. So it's going to be a constant volume. You really just got to find the pressure. This is going to involve some basic Stoic. And it's really helpful here to put a table down. So let's draw a table. Let's actually put our reactants. We have NO, we have O2, and we have our product NO2. So put a table here like this, and then you can call one part of it before the reaction and one part after the reaction. You can also use 1s and 2s, whatever you want to do, but I'm just putting B for before and then A for after. Before the reaction starts, there will be some amount of nitrogen monoxide and some amount of oxygen, and there will be no product yet because the reaction hasn't technically started. Afterwards, we need to figure out, well, how much product do we have? There's going to be some number of moles of product produced. And there may be some moles of unused reactants. That means we're going to have to rely on our limiting reactant knowledge as well. We do know, though, that initially we have 2 moles of the nitrogen monoxide and 2 moles of the oxygen. So we're going to figure out that last part. Here, you need to do some basic Stoic with limiting reactants. It's going to look like this. Let's deal with the nitrogen monoxide first. If I have 2 moles of NO, and we ignore the oxygen for a second, I'm going to go from moles of nitrogen monoxide to moles of nitrogen dioxide. And according to the balanced equation, it's a 2-to-2 ratio, which means that with nitrogen monoxide, we could get 2 moles of NO2. Now, like we've done before with limiting reactants, let's go to the oxygen. If I have 2 moles of oxygen, and I convert that from moles of oxygen to moles of the product, which is NO2, I see that there is 1 mole of oxygen for every 2 moles of nitrogen dioxide, and I get 2 times 2, which is 4 moles. So remember, for limiting reactant problems, you have to look at what you're literally given. This reaction can only start with 2 moles of nitrogen monoxide and 2 moles of oxygen, which means that we have to run our stoichiometry through for both reactants, and we see that we can either get 2 moles of nitrogen dioxide, that should not say oxygen, let's just say nitrogen dioxide. So we can either get 2 moles of nitrogen dioxide or 4 moles of nitrogen dioxide. Turns out that you have to go with the lowest number. So with the 2 moles of the reactants each, you can only get 2 moles of nitrogen dioxide. The nitrogen dioxide is going to be your limiting reactant, and the oxygen will not run out first. Notice how the oxygen, there's plenty of oxygen to give us more carbon or more nitrogen dioxide. But because of this more limited amount of nitrogen monoxide, it's our limiting reactant, and therefore the oxygen is your excess. Now, what that means in reality for a rigid container is that the oxygen's still going to be there. Some of this excess oxygen will not be used up, but it will remain in the container as a gas. It doesn't just disappear. So we are going to get rid of all of this, and we say, well, the maximum amount of nitrogen dioxide that we can actually make, so we're going to put it here in the after part, is really just 2 moles. These are all moles, by the way. So all of these numbers are representing moles. This is our actual amount. So if you remember how limiting reactants or limiting reagents work, one of them will run out before the other one, and the other one will still just be around. In this case, we have some excess oxygen. We can work backwards to figure out exactly how much excess oxygen there is. So to do that, let's work these numbers backwards. Doesn't matter the color. But if we have 2 moles of NO2 actually made, right? So now we're dealing with the actual situation. We're running it backwards. If we have 2 moles of nitrogen dioxide made, we want to know, well, how much of the actual oxygen would that require? So I'm going to put moles of NO2 at the bottom, and I'm going to go to moles of oxygen. I know this can be a lot, so I'm going to review what I just did. First, I used the principles of limiting reactants to do double stoichiometry to figure out how much NO2 can I actually make, given these 2 quantities given here. Turns out that the NO2 will run out first and give us a relatively lower amount of NO, or the NO will run out first, giving us a relatively lower amount of NO2 product. Since I can only make 2 moles of NO2 because there's not enough NO to make more of it, that's my actual amount of NO2 I can make. So what I'm doing here in blue is I'm figuring out how much oxygen is actually consumed and locked away into the NO2. So this reaction shows that for every 2 moles of NO2, it requires just 1 mole of oxygen. And if you do your math here, 2 times 1 is 2, divided by 2 is 1. So you get 1 mole of oxygen actually used. Now let's think about that. There are 2 moles of oxygen available at the start of the reaction. When the NO runs out, so when our limiting reactant, which is the nitrogen monoxide, runs out, we only were actually able to use a single mole of oxygen. So of the 2 moles of oxygen available, 1 mole of oxygen was locked away into the product, and the other mole of oxygen is still floating around. So let's put that in here. Remember, the NO is our limiting reactant, so it will run out to 0. Let's put that in red or black, doesn't matter. It will run out to 0. But what we do understand also is that in the after, how much actual oxygen is remaining? Just a single mole. So 1 mole actually used, 1 mole unused O2. This after part is important because it tells us the total number of moles. So add up the total number of moles here, and let's see how many total number of moles we get. After the reaction has completed, there is no more NO remaining, there is 1 mole of unused oxygen remaining, and the amount of NO2 created was 2 moles. That means that there's a total number of moles, so N subscript T for total, of 3 moles of gas in this reaction. So what that means is you can plug that into, whoops, didn't mean to shrink the whole page. You can plug that into the ideal gas law equation, and you'll get that the pressure is equal to N, which is 3. We figured out that there are 3 moles. R is 0.0821. The temperature is 298 Kelvin. And all that divided by the total volume, which is locked in at 25 liters. And you're going to get, what did I get? 2.94 ATM. And that's how you get that answer. For number 13, it says consider the following phosphates. Which of the following phosphates are water soluble? You just have to know your solubility rules. It just depends on your professor. Some people have moved on from memorizing them. Some people still require people to memorize them. So let's add our solubility rules table. According to the solubility rules, since all of these are phosphates, you got to find phosphates. Phosphates are going to be in this line. So let's look at phosphates. Phosphates are not soluble unless those phosphates are with something from group 1 or ammonium. So let's check them out. Silver, that's not in group 1, so that one's not going to fly. Silver phosphate will be insoluble because it's not group 1. The silver is not in group 1, and ammonium is. So if you look at the cations, the cation here, silver, is not group 1 and is not ammonium. What about calcium? Calcium phosphate falls into the every other phosphate category. Calcium is not group 1 and is not ammonium, not soluble. Ammonium phosphate is one of our exceptions. It is soluble. And then aluminum is not group 1 and it's also not ammonium. So it's not soluble. So it's just one. So only the aluminum phosphate only the ammonium phosphate is soluble based on the rules. The other ones are not soluble. So that one's just looking at your solubility rules, and maybe you'll have that as a reference, not sure. Number 14. The beakers contain aqueous solutions of lithium carbonate. Which beaker best represents the compound in solution? Water molecules are not shown. So this also comes back to your solubility rules. This is lithium, which is in group 1, and then carbonate. So look back at the solubility rules. Now we're dealing with the carbonate aspect. But same thing applies, except now we know that carbonates are just not soluble unless they are with something from group 1, which lithium is. Lithium is in group 1, so that would make lithium soluble. So if you dunk in some lithium carbonate, which is LiCO3, and that'd be a 2 here. So if you dump in some lithium carbonate, it does help to have your naming down. Think about what happens if you have some solid lithium carbonate and it dissociates in water. You'll get 2 moles of the lithium plus ion, which is going to be aqueous, right? It'll be dissolved. And you'll get 1 mole of the carbonate ion. So color coding this, the carbonate ion is going to be red in all of these. And then the lithium ion, they're using like this orangey brown color for those. Looking at your ions, think about the fact that you will have 2 lithium ions for every 1 carbonate ion, right? Which means that since it completely dissociates, you better have twice as many lithiums as carbonates. So here's a lithium, a little positive lithium, 1, 2, 3, 4, 5, 6. So there are 6 lithium ions. Over here though, there would just be 1, 2, 3. So there'll only be 3 lithium ions. So looking at your ratios, you got to keep going with them and see what is going to play out. In C, you have 1, 2, 3 carbonate ions. So 3 CO3, 2 minuses. And then on the other side, you have way too many. So looking at here, you have 1, 2, 3, 4, 5, 6. So it's really just about counting up and looking at your ratios. 6 carbonate ions over here. Which one of these looks correct? First one's out. A is out because if lithium carbonate were insoluble, then you would see it go in kind of like just chunks of solid. But since lithium carbonate is soluble per the solubility rules, it's going to completely dissociate, which means it'll break apart. And you can see right from the equation that you'd better have twice as many lithium ions as carbonate ions, because that's how it breaks apart with the number of ions. So the one that's correct would be C. So beaker C is correct because it has twice as many lithiums as carbonates per the dissociation equation. 15. Which of the following aqueous solutions are a weak electrolyte? So an electrolyte is going to be an acid, a base, or an ionic compound that dissociates. Now they can come in 2 varieties, weak or strong. You do have to memorize your strong acids and realize that everything else is weak. One of the main things that I immediately am recognizing now is that HF is weak. It is a weak acid, so it's going to be a weak electrolyte as well. So since it's a weak electrolyte, you better have that in your answers. this comes back to just kind of reviewing your notes. Iron 3 chloride, looking at the solubility rules, chloride is soluble unless they're with one of those things. So this is a strong electrolyte. I'll put WF for weak and SF for strong. So this is going to be a weak why am I putting F? E. There we go. This is a weak electrolyte, HF. So this should be in your answer. Iron 3 chloride would be considered a strong electrolyte. Magnesium sulfate, sulfates. So go back up to your solubility rules. Sulfates are soluble unless they're not, with those exceptions. But it turns out that magnesium sulfate is soluble. So because it's soluble, it would be considered a strong electrolyte. HBr is considered a strong acid. So because it's a strong acid, it's a strong electrolyte. So you don't want to have that one checked either. This is ethanol. Ethanol is very, very incredibly weak in terms of its acidity. Like that hydrogen ion here is just not going to dissociate very much. It has a pKa value that's like going to basically say it's going to stick to be ethanol. So this is a very weak electrolyte. And it's basically not an electrolyte at all. It's like super duper weak. It's just not an electrolyte effectively. And then you have H2S. That is going to be a weak electrolyte as well because it's not a strong acid. So looking at this information, put a little check mark here and here. It says which ones are you going to want? You have 1, you have 6, and then technically because this is a molecular compound, I'm actually going to call it a non-electrolyte because it's molecular. And by that same logic, H2S is also a molecular compound, but it still can act as an acid, just not a very strong one, so it's a weak electrolyte. So the one that makes sense is going to be 1 and 6. But theoretically, 5 could work as well, as long as you definitely have 1 being a weak electrolyte, and then this one being a weak electrolyte. And the dissociation of the hydrogen ion, or the dissociation of hydrogen in ethanol is so small that it's basically a non-electrolyte. So I would say 1 and 6. But there's a lot of gray area in chemistry. So that one, a little bit iffy on that one. In terms of whether you would consider 5 to be an electrolyte or not. Okay, 16. What is the density of hydrogen sulfide gas, H2S, at 45 degrees Celsius and 1.21 atm? So we may as well just derive the density versus like the ideal gas density equation connection thing. Density, and I'll use rho for density. Density is equal to mass over volume. And in the ideal gas equation, PV equals nRT. So solving for V here, we get that V is equal to M over rho, which is density. Make sure my rho does not look like a P. This is a capital P. This is a Greek letter rho. Which means we can actually do a substitution. So P times M over rho is equal to nRT. Now it does say what is the density of the ideal gas. So we ultimately need to solve for rho anyways. So to do that, we're going to use the rules of math. We'll basically say that on this side, we effectively have P times M over rho equals nRT. So just divide and do your mathy stuff. And you divide both sides by M and by P. And what you get is this. Divide both sides by P and M. Then you get 1 over here. You can flip it all, and then you get rho is equal to P times M divided by N times R times T. But then you gotta recognize something. Something that I think is kind of neat is that M and N, so M is for mass and N is for moles, that actually means molar mass. If you look at your units here, kind of do a unit inspection, pressure atm. Moles, or mass, is going to be grams. Your N is going to be moles. R is going to be atmosphere liters per mole Kelvin. And then T is Kelvin. So looking at some stuff that's going to cancel and not cancel, we effectively want density to just be grams per liter. So let's see if everything cancels out. Atmosphere's gone top and bottom. Kelvin gone here and here. And then grams per mole is actually going to be molar mass. So we can kind of just put grams per mole out to the side there. But it still will cancel out. And ultimately what we get is grams per liter, which makes sense. Grams per liter. That means that all we got to do to tighten this up is take this red stuff and make it our molar mass, which will pop up toward the top. And molar mass has a bunch of symbols, sometimes like that weird cursive looking M thing. I write capital M, does not matter. So here's the equation. Here's how the derivation for the density of a gas can be understood. That was just showing you how it comes to be. So we don't need all this other stuff now. We only need the final derived version. So what we have here is it says the density of a gas is equal to the pressure times the molar mass divided by R times T. Let's plug in everything we got. The pressure is given as 1.21 atm. The molar mass of H2S you can easily find. It's going to be 34. Let me just look real quick. So 34. Sulfur has a molar mass of 32 plus 2 is 34. So it's about 34. You can just say that. 34.1-ish. And then R is 0.0821. And then the temperature is 47. But we got to add 273. You get 320. And then when you do the math here, you get 1.21 times 34-ish divided by the product of 0.0821 times 320, and I get about 1.57. So about 1.57 grams per liter. Remember, those are going to be your derived units for the density of a gas under non-standard or standard conditions. In this case, we have non-standard conditions. Notice how the temperature and the pressure are not standard. So that's why this equation is useful. Okay, and then 17. How many of the following compounds produce 3 ions per formula when dissolved in water? So when you're looking at these, I'll probably go back and circle the answer for the last one. It's that one. For number 17, when you're looking at them, Na2SO4, you need to know your solubility rules. So have them up here. Sulfates are soluble unless they're with something that's not. So sulfates are going to be soluble, along with the fact that group 1 ions like sodium are almost always they're just soluble. So for the first one, I guess I'll list them out. For the first one, you get Na2SO4. I'm going to omit the states because it's not important right now. And it's going to become 2 Na ions, so 2 Na pluses, and a single sulfate. For the second one, calcium sulfite. Calcium sulfite, I don't even think sulfites are on here. No. So because it's not on there, and also even if it were, even if it is completely soluble, it's still not going to give you 3 ions per formula. Here's why. Assuming it's soluble, which it isn't, it doesn't seem, I don't know. But even if, whether it is or isn't, is important because look at it. If you do break it apart, you get 1 calcium 2 plus and 1 sulfite. So count your total number up. 2 ions plus 1 ion. That's going to give you 3 ions for the first one. For the second one, 1 ion plus 1 ion gives you just 2 ions. And that's assuming it is soluble in the first place. F2O. So this is going to be a molecular compound. So F2O just becomes F2O, no ions. So we're going to say none. For H2O, same thing. It's molecular, and it's technically an acid and a base, but also neither, so there's going to be no ions. No net number of ions. So we're going to say none. And then lastly, we've got calcium nitrate. So calcium NO32. From our solubility rules, we know that nitrates are very soluble. So you'd get a calcium 2 plus ion and 2 nitrate ions. That'd give you 3. So only 2 of them. Which 2? The first one and the last one. That's why the answer is just 2 of them.